Thanks so much, Jamie. It's wonderful to be here, and thanks to everybody who's here. I hope this talk will generate some interesting discussion. I am presenting a new interpretation of quantum theory here. That's an ambitious and maybe foolhardy project, but I figure, it would be worthwhile to try to introduce, new ideas and to make positive contributions to this discussion. There's a lot of critiquing that we do of each other in this field, and that's all great. This is my attempt to actually introduce something, hopefully that's new. All right, so I'm going to get started. The picture here from Magritte will play a role, as we'll see. All right, so outline of this talk. I'll start with a brief introduction, some motivation. I'll talk about the classical case, highlighting features of classical physics that will be relevant to the discussion of the quantum case that I'll cover next. And then I'll talk about the measurement process, both in the classical case and the quantum case, before moving on to the conclusion. I think a place to start is with this Emily Dickinson poem. It's one of my favorite ones. We send the wave to find the wave, an errand so divine, the messenger enamored to forgetting to return. We make the wise distinction still, so ever made in vain, the sage's time to damn the sea is when the sea is gone. What are we doing if not sending the wave to find the wave? All right, so it's a little bit of history. And this is all review. I'll go pretty quickly through this because this is stuff that most of you probably are very familiar with. So, as we know, quantum theory is the most empirically successful scientific framework in human history, but after a century, there's still no consensus over its proper physical interpretation. Since about 2017, I've become increasingly interested in the Gelfand-Neymark Siegel or GNS construction, both for foundational and pedagogical reasons. Roughly speaking, and one of the things that got me so interested in this is the GNS construction implies that once you have enough starting ingredients, the Hilbert space picture of quantum theory emerges sort of automatically. There's some technical subtleties here. But what it led me to do was rethink the status and the role of the Hilbert space picture. I mean, think about how, I know we take this for granted at this point, but if you stop and think about it, right? The objects in the Hilbert space picture, wave functions, self-adjoint linear operators, Hilbert spaces, these are bizarre and difficult to interpret. The GNS construction, from my point of view, suggests that maybe we shouldn't read too much into them. I gave a talk at the BHI Foundation seminar a number of months ago on the GNS construction more specifically and ideas related to that. So in some ways, this is kind of a follow-up to that talk. Anyway, the GNS construction suggests that maybe we shouldn't read too much into the objects of the Hilbert space picture. The Hilbert space picture is not wholly writ. It's a paradigm. And the moment you realize it's a paradigm, maybe you have an instinct that maybe we should think more carefully about how much we want to buy into it. And the name of this interpretive approach, or this program that I've been working on, is sort of inspired from this by the idea that the Hilbert space picture is somewhat akin to like the shadows of Plato's cave. And in this analogy, the GNS construction is like the fire that casts those shadows. There's a prominent role in this interpretive program played by certain mathematical ingredients. The chief one is C-star algebras. Not everybody here may be familiar with C-star algebra. Some of you are, some of you aren't. I'll try to split the difference and explain the degree to which I need this material. But C-star algebras are widely used in the algebraic quantum field theory community, also by some philosophers of physics, and by mathematicians who work on function analysis. But I can tell you from personal experience, having worked in the Harvard physics department for almost 20 years, C-star algebras are not widely used or understood or known, the GNS construction and so forth, in the physics community. So this is my key takeaway slide. There's a lot on here, but I wanted it all to fit on one slide. It is a whole interpretive program, so like there's a number of items here. So what are the key takeaways? What is the key thrust of the Platonic interpretation? The first is that we will identify certain elements of the system's C-star algebra as having an ontic meaning, as corresponding to ontic properties, things that actually exist. We'll encode the system's epistemic and gnomic data, what can be known, the degree to what can be known, probabilities, information about relationships between probabilities, and the rules, the laws, that's the gnomic data, as a special class of maps on the C-star algebra. These are the state maps, for those of you who are familiar. We will allow that some familiar features of classical probability theory can break down. We have to bite the bullet somewhere, and the idea is that we're biting the bullet on the epistemic gnomic side and not on the ontological side. In particular, we'll assume that joint probabilities exist only to the degree that not only do you have commutivity between the relevant elements of the C-star algebra, but also when there's no direct entanglement between them, which is a novel ingredient as far as I can see in quantum foundations. When we discuss the measurement process, I'll explain that from this point of view, decoherence is a physical process. It physically changes things, but collapse of the state vector, collapse of the state map, we'll see as a subjective or perspectival conditionalization, not a physical process. The genus construction generates the Hilbert space picture for free. So, the mentality here is that the Hilbert space picture will be something like a software layer, a convenient, useful set of mathematical tools, like the Hamiltonian phase space formulation of classical physics, and other ways to reformulate classical physics that we'll discuss. All right, that's the introduction. Now, motivation. So, why was I motivated to go in this direction? Let's stop for a minute and talk about classical physics. So, you don't have to do this, but if you choose to do this, you can do it in an intellectually honest way. You can regard a physical system, like a bunch of particles, say, or a bunch of electric fields, as existing in 3D space, consisting maybe of material bodies moving along definite trajectories, or field intensities varying in strength at localized points. There are, of course, subtleties when you consider gauge theories. I'm going to put those subtleties aside for now. So that's a picture you can choose if you wanted, a picture with a clear, as we would say, ontology. There's stuff out there, and we have a mathematical description of it. In quantum theory, the Dirac-von Neumann axioms paint a far murkier picture of reality. And again, this is review. So on the kinematical side, these axioms say that all contingent facts about a given quantum system are encoded in a mathematical state vector, depicted here as ket side, a sort of notation, like Brock-ket notation, in a Hilbert space, which is a complete inner product space over the complex numbers. It's got an inner product. And on the dynamical side, there exists a Hamiltonian, a special self-adjoint operator for which the state vector evolves according to the Schrodinger equation. All of this applies if the system is closed. It's not exchanging information with other systems. Things get much more complicated when you have an open system. You get trouble right away. In this case, you're generically going to get entanglement, a lack of factorization of state vectors between the system in question and the other systems it may be interacting with. And in particular, this means that your open system itself will not generically have a state vector. You have to instead use a density operator obtained from partial tracing. It's the reduced density operator. And in general, it evolves according to a much more complicated dynamical equation. There's a whole class of these equations called master equations. And these generally just keep generating more and more entanglement. If your open system has a lot of degrees of freedom and the environment around it has a lot of degrees of freedom, generically, you'll just get more and more entanglement as things develop quite rapidly. And in fact, this is a big problem with quantum computing, because if you have a quantum computer, you don't want this entanglement to be happening. And the more qubits you have in your quantum computer, the far greater likelihood is that you'll get a lot of entanglement with the environment. So then on the other hand, there's the measurement axioms. The measurement axioms connect this mathematical formalism to empirical results, and they, if anything, make the story even worse. In the simplest case, every observable feature of your system corresponds to some, I'll use a symbol, capital A for it, and that's represented by a self-adjoint linear operator on the system's Hilbert space. The possible measurement results correspond to its eigenvalues. Here I'll use a label, little letter A, to identify the different eigenvalues, capital A of A. So think of A as just an index saying which eigenvalue we want. The capital A of A's are not necessarily all distinct. So in the case where your system is described by a state vector, like it's a closed system maybe, and we know the exact state vector of the system, well, then there's the standard formalism, right? We introduce a notation for the eigenvectors of A. We introduce notation for the projectors, the eigenprojectors of A. They're outer products of these, the rank 1 outer products of these eigenvectors. And then, we can compute the probability according to the measurement axioms from the Born rule. You either take the inner product of the appropriate eigenvector with the system state vector, take the absolute value squared, or you sandwich the projection operator between bra and ket of your state vector. And A itself, the observable in question, has expectation value given by this sandwiching formula. If the system is described by a density operator, then you have to you write things in a somewhat different way. You take the trace of the density operator multiplying the projection operator. And to get the expectation value of A itself, you take the trace of the density operator against the operator representing the observable. If the state vector, again, considered in case of a specific state vector, has unit probability for a measurement of the observable A to yield the specific result A of little a, with probability 1, then the state vector has to be an eigenvector of A with eigenvalue A of A. This is the so-called eigenvector eigenvalue link, or eigenstate eigenvalue link. Immediately following the measurement, the state vector or density operator collapses to the eigenvector corresponding to the observed measurement result. And this ensures robust results under repeated measurements because, again, we now have the eigenstate eigenvector link applying. If I immediately do another measurement at this point, I'll get the same result, as long as I don't give the system time to evolve, maybe unitarily or by a master equation to something else. All right, so just an example that will illustrate all of this. Again, this is a review, I'm sure, for essentially all of you, but we'll also just introduce some more objects into the story that will be useful later. So if Q, capital Q, represents a classical-like configuration, like a particle position or a field intensity, I'm being a little schematic here, then a system with a state vector psi has a wave function, which is defined by taking the inner product of psi with this eigenvector. This is a function of little q. And then the absolute value squared of this wave function tells you the probability of finding the system in that particular configuration. It's actually a probability density if Q is a continuous kind of observable. The wave function of a system lives in configuration space. It's a map from configuration space to complex numbers. And so for a system of n distinguishable particles in 3D, it's a 3n dimensional space, and not to be confused with physical space. So what's the measurement problem in a nutshell? Well, on the one hand, we have standard time evolution. For the closed system, it's the Schrodinger equation. For open system, it's some more general master equation. Neither kind singles out a definite measurement result, right? On the other hand, when you do a measurement, you get collapse to a definite measurement result. No measurement is exactly perfect, so you might not get collapse to an exactly perfect measurement result, but you do get a collapse to at least close to an approximation to a definite measurement result. And these are just very different kinds of behavior. Moreover, the Dirac-von Neumann axioms don't rigorously define what physically constitutes a measurement. Like, when do we use one form of evolution over another? We just declare it, but it's not built into the formalism to tell you when. It's just something observers, however they're defined, do, however defined. Decoherence was, considered for a long time a very promising avenue for maybe helping resolve this question, but it can't rescue us from this problem. Right, decoherence is the tendency of environmental interactions to make a density operator evolve rapidly into a form that does mathematically resemble a classical probability distribution for certain observables, but it doesn't single out definite measurement outcomes. It yields what are called improper mixtures, which, for all kinds of reasons going back to Schrodinger in the 1930s, don't have a simple interpretation as just encoding totally subjective classical type ignorance. And moreover, collapse can be non-local. Famously, if you just naively apply the collapse postulate to EPR type setups, you get what seem like manifestly non-local behavior. But decoherence is a local dynamical process thanks to the no signaling, no communication theorem. So there have been attempts over the years to try to concoct a sufficiently complicated dynamical mechanism that would make it look like you're getting collapse, but there's just no way to get around this non-locality issue. You're not going to replicate what we see as standard textbook collapse this way. All right, so now this motivates us to maybe try to find some other way of thinking about quantum theory, maybe reinterpreting it, maybe modifying the theory. And in particular, I would argue, and has been argued before by others, that an interpretation of quantum theory, and some would call this a proper theory of quantum theory, should resolve the measurement problem and should ideally also have an ontology, a statement about what actually exists. That it shouldn't just be a prescription for saying what observers see, that it should have an epistemology. Roughly speaking, it should be able to describe what we know, what we can know, to what degree, maybe using the language probabilities, and a nomology, the gnomic sector. What are the laws that summarize or govern the behavior, depending on your view on the nature of laws? So I'm going to do a quick lightning tour of the other interpretations that are prominent and why they're dissatisfying to me. So there's a Copenhagen interpretation to the extent that it's a well-defined, agreed-upon interpretation to begin with. Roughly speaking, and I've definitely heard prominent people describe it this way. On the one hand, you have macroscopic classical systems and you have microscopic quantum systems. When classical systems evolve on their own, they evolve classically. Quantum systems evolve according to the Schrodinger equation or open dynamical, open master equation. When classical systems interact with quantum systems, then you get a collapse. And there's this Heisenberg cut, this abstract dividing line that divides the two, but this is completely ad hoc. The de Broglie-Bohm and Bohmian mechanical formulations, and there are some actually subtle differences between these two, but I'll lump them together for present purposes. They say that you take the standard formalism, the Hilbert space formalism, and you supplement it with some additional hidden variables that have an ontic nature that encode ontic information, particle positions if you're studying particles, if you're studying bosonic fields, their intensities. And the idea is, and the way that this actually happens is, people take the quantum formalism, they look at the wave functions, they look at the configuration space the wave functions are defined on, and they try to interpret that configuration space ontically. They take the parameters that describe that configuration space, whether they're particle-like degrees of freedom or bosonic field intensities, and they reify them and treat them as ontic things. And then you regard the wave function itself, which is in the formalism, as an ontic thing, a pilot wave that physically exists and guides things around. Or another point of view is that it's more of nomology. The wave function plays a role kind of like a Hamiltonian that governs how things evolve. There are major problems with relativity in this approach. I've never seen a satisfactory, fully relativistic, special relativistic treatment of Bohmian mechanics. There's also trouble with systems that don't seem to have configuration spaces. Fermionic fields are a very good example of this. There is no wave function on anything like a familiar kind of real valued continuous configuration space for fermionic fields. And so these are a major stumbling block for this approach. There's the Everett many worlds approach. You shrink the ontology down to just the universal wave function, the homology down to just the Schrodinger equation for the universal wave function, and claim that the familiar world as we know it arises in the sense of branches of this wave function in an emergent sense. Emergence kind of plays the role of the Heisenberg cut. But it's hard to make sense of probability. I don't have to go over this. I'm sure a lot of you have problems with the way that probability is understood in this approach. And there are claims you can derive probability this way, which I have deep problems with. A deductive argument should have probability inherent in the premises, which is assumed not to be the case. An inductive argument already assumes certain a priori notions of probability. I'm not sure how you get off the ground with this approach. You also have many maverick branches that are produced. They're produced in large numbers. Maverick branches that are, not observably consistent with the Born rule. And so the whole thing becomes, in my opinion, self-undermining. The statement that we see the Born rule becomes circular. We see the Born rule because we're on a branch in which the Born rule is observed. This doesn't seem very satisfying to me. Then there's the spontaneous collapse approaches like GRW that actually modify the dynamical rules of quantum theory. You may have ontic wave functions. There may be physical collapse events. There are flash ontologies. There's mass ontologies. And the idea is that these collapse events are rare at an individual particle level, but when particles get entangled, they become much more common. But these introduce ad hoc parameters that describe the rate of collapse. They're difficult to reconcile with relativity. And then there's the instrumentalist approaches, orthodox quantum mechanics, cubism, quantum Bayesianism. And in these approaches, the observer is an abstract agent, which as far as I'm concerned is just another word for observer. So that doesn't really bother you very much. And you're just quiet about the ontology. Right? The observer is using this formalism to make predictions, but they'll see. But this is, in my opinion, very incomplete. Like, are agents ontic? Where are they in the formalism? What about their ontology is encoded anywhere in the formalism? What are the probabilities that they're computing probabilities of? Are they probabilities of measurement results? But measurement results are recorded in the state of the observer. But if a state is just a collection of probabilities, again, there's a circularity sort of built into here. What's the underlying problem behind all these? In my opinion, the underlying problem is, or one of the underlying problems, a significant one, is the assumption of a fundamental status for the Hilbert space picture. State vectors, wave functions, density operators, self-adjoint linear operators, inner products. This is a lot of baggage. These are very exotic, difficult to interpret ingredients. And if we take them as prior, we're going to run into all kinds of conundrums trying to make sense of what's going on. Again, this paradigm is not sacrosanct. I believe it merits a critical reevaluation. Here I quote von Neumann. I don't know that he was thinking exactly along these lines, but I do take this to be sort of an inspiration for my thinking here. I would like to make a confession, which may seem immoral. I do not believe in Hilbert spaces anymore. With apologies to Magritte. Ceci n'est pas honnête, if I pronounced that correctly, which I probably didn't. Right? This is not a state. Okay, it's something written on a piece of paper. All right, so what I'll do in this talk is we'll start in a different starting place, and I'll argue that one can derive quantum theory from a sharp ontology consisting of physical systems with basic properties, but that exhibit a more non-trivial probability structure than one finds in the classical case, and that this leads to a neurointerpretation, the Platonic interpretation. So here's a summary. The ontology is going to say that there are physical states of being, ontic states of your system, that are characterized by ontic properties with quantifiable underlying values. In this sense, very similar to classical physics. The epistemology is going to consist of individual probability distributions for these things, but also subtle interdependencies between these probability distributions. These are relationships between probability distributions. And these probability distributions, their relationships characterize the degree to which those underlying values are manifest to the outside world. You can think of this, and I'll explain what I mean by manifest in a moment, but if you want, you can also regard this in the frequentist sense. You know, that there's limited information about certain ontic properties of the system, and in some frequentist sense, it means if you have similar systems, some of them will be like this, some of them will be like that. I'm not going to take on the philosophy of probability in this talk. This is, I'm going to punt on the question of what probability fundamentally means, one problem at a time, please. And the nomology, the gnomic sector, what the laws are, they're going to be subtle, but ultimately there'll be a codifiable collection of rules for all these foregoing ingredients. Let me say a quick word about manifestness. And again, if you don't buy into this idea, that's fine. It's not crucial. It's just one way that I like to think about the epistemology of this approach. So in 1935, Schrödinger said there's a difference between a shaky or out of focus photograph on the one hand, and a snapshot of clouds and fog banks. There is an attitude in quantum foundations to say that when you have something foggy, it means the ontology is ill-defined or foggy. I'm going to argue that no, if things look foggy, the ontology may be fine and sharp. It may just be that there are limitations to how well the external world can see things. Right? And this means that epistemology is not wholly subjective. It's not just a personal, lack of knowledge or whatever, but there's an objective aspect to it. There is an empirical sense in which certain situations, there's only so much that can be known without interfering or interacting or perturbing the system in question. In a sense, what we're going to be doing is shifting the weirdness of quantum theory from the ontic sector over to the epistemic gnomic sectors in some loose sense. So what obstructs full manifestness of the system's ontology? Why in certain situations might you not be able to see clearly the sharp underlying ontology? Well, the keynote idea here is that, well, ontic properties generically need not share a meaningfully correct overarching joint probability distribution. That's the claim. The claim is, in the Platonic interpretation, that ontic properties share a valid joint probability distribution if they commute, and that first step, that's a lot of people, already know and are take that seriously. That if two things don't commute, then you can't put a well-defined joint probability distribution. That gets the door open, as far as I'm concerned. But the second thing is that when there's significant direct entanglement between them, that's also an obstruction to the existence of a well-defined joint probability distribution. It's not something that I've seen discussed in literature. And I'll explain in more detail what I mean by this and what role it plays, in particular in the measurement process, when we get to the later part of this talk. All right, so, and the idea of how measurements work, and we'll go into some more detail later, is that measurements involve interacting, between interactions between some kind of measurement device, its pointer variable, and some, feature of the subject system to be studied. And then there's environmental decoherence. And that environmental decoherence is a physical process that will break direct entanglements between the subject system and the apparatus measuring it. And it's that moment when you break that direct entanglement that joint probability distributions will emerge between the measurement device, what its reading is, and the outcome. All right, so from this point of view, the Hilbert space picture again plays the role kind of as a software layer, like the Hamiltonian phase space formulation, or as we'll see, the Kupeman von Neumann formulation of classical physics. This is not super well known, but it is very useful. We'll talk about it later. The idea is the Hilbert space picture is no longer a fundamental physical aspect of reality. We don't have to stare at a state vector and go, there's a state vector, we have to interpret it. What do all its branches mean? They're just there. Well, I would caution against that. So we'll do the classical case first. This will set up some concepts and terminology, mathematical structures that we'll find useful in the quantum case. So again, the ontology of a classical system, if we wish, we could imagine that a given classical system has properties that define the system's ontology, ontic properties. Each of the system's mutually exclusive ontic states, each distinguishable mutually exclusive ontic state of the system that tells you, that contains the properties of that system. It specifies all the values of the property. So examples again would be, like for mechanics of particles, these could be the positions of momentum of the particles. For fields, local intensities and rates of change. Practically speaking, we don't always know the values of those properties with certainty. So our epistemology, or if you want, our epistemic state, is captured by an overall probability distribution. Probabilities associated with those ontic states, they have the usual probability behaviors. Here I'm, for mathematical simplicity, assuming a discrete set of ontic states, just so I don't have to worry about integrals and so forth. And this means the ontic states constitute a sample space. It's a set of points that a probability distribution lives on that satisfies the usual probability axioms. We can associate each ontic property with a symbol, A, if you will, that stands for its list of possible, although not necessarily distinct, real values. In this case, they're labeled by the system's underlying ontic state, and they have probabilities given by the epistemic state of the system P. We then call A a random variable, a list of possible outcomes, a list of possible values with associated probabilities. We can also define algebraic combinations of random variables. We can add them together, multiply them, and so forth. We can define more general functions of them. And these have the standard meanings. Our collection of random variables is then said to form an algebra. A particularly important collection of elements of this algebra are the elementary projectors. If you're given a particular ontic state of the system, you can associate a random variable that just asks the question, is the system's ontic state x naught true, 1, or false, 0? So this is represented by the Kronecker delta function. We call it an elementary projector. And these satisfy a number of nice properties. They are mutually exclusive. You multiply them together, you get back one of them up to a Kronecker delta. They're complete. You add them all together over all the possible values of x, you get the identity random variable I. And for all the random variables, they satisfy an eigenvalue equation and a spectral resolution. You can express any other random variable as a linear combination of them with the underlying values of that random variable appearing as the coefficients. We can generalize this notion. If you take the sample space and consider subsets of it, E and F, we can introduce projectors onto those subsets, and they automatically satisfy this nice identity that when you multiply two of them together, you get the projector onto the set theoretic intersection. Notice, set theoretic intersections are commutative, and this is compatible with the fact that these projectors are commutative. We'll come back to that point later. It's convenient to introduce complex numbers if we wish. They're very useful in classical physics for all kinds of reasons. And once we do this, it's natural to introduce an operation on the random variables, the star operation, which cashes out in this classical case to just simple complex conjugation. Okay. We can define a norm as the supremum among the absolute values of all of the possible underlying values of each of these random variables. We can use this norm to introduce notions of limits and continuity. We can extend our algebra by including all limit points of Cauchy sequences. This makes it closed in a topological sense, and so we end up with a closed star algebra, a C-star algebra. That's what it is. That's where it comes from. If you haven't seen these before, this is what they are. Now we have the epistemic state for the system as well. We can abstract that also and lift it up to the level of the C-star algebra by introducing what's called the state map. State map is a map on the C-star algebra that takes each element of the C-star algebra and simply outputs the expectation value. You can get back the original probability distribution itself by simply acting on one of the elementary projectors. So this contains all the information we had before. We can also use this to obtain probabilities of subsets of the sample space. We can get joint probabilities this way. We can build everything we want out of these state maps. We can build statistical quantities of interest, covariances, standard deviations. This is all hopefully stuff that people have seen before. All right, so when you have a C-star algebra and you have a state map that satisfies a collection of basic desiderata, normalization, linearity, positivity, these are all satisfied in our classical case. Then the Gelfanding Mark-Siegel, the GNS construction, says that you automatically have a Hilbert space. Your state map goes over to a state vector in this Hilbert space. Classical random variables become, in this case, commuting, in this classical case, operators A. And there's a simple relationship, the dictionary, the GNS dictionary that takes you between the GNS story and the Hilbert space story, that says you can compute expectation values, as sandwiching the corresponding linear operators between system, state, vector, broad ket. Does this look familiar? I mean, this is the Born rule. But what we see from this classical story is that, well, we could have introduced Hilbert spaces, but we didn't have to. They weren't fundamental. They're convenient, at least in some cases. When you do this in the classical case, you get what's called the Kupeman von Neumann formulation, which goes back, almost a century at this point. And this is actually useful for studying ergodicity and dynamical systems and chaos. And there's some cute things you can do with this, like you can use the Cauchy-Schwarz inequality on the Hilbert space picture of the classical story to derive well-known bounds on covariances and correlations. This is actually the way that I usually, teach those things when I teach these subjects. I find that this is the most simple, direct way to do it. But the Kupeman von Neumann formulation also contains lots of strange, exotic, non-ontic ingredients. I mean, it's a Hilbert space. You can introduce operators in it that live in this Hilbert space that don't commute with things. What interpretation do these things have? You can only imagine if we discovered classical mechanics this way, we'd be sitting scratching our heads wondering what to make of all of the weird objects in the story. Well, given the Hilbert space picture emerges automatically, I think the more natural thing is to be suspicious that it means too much in the classical case, and that's maybe a lesson for the quantum case that's coming next. So, what is the thing we change to get to the quantum case? Well, we generalize. One way to generalize is to drop the assumption that ontic states form a valid sample space, that we don't assume that there is a valid joint probability distribution P over, over those ontic possibilities. But note, this move is a matter of epistemology, not ontology. We're not saying that there are no ontic states or no ontic properties. We're just saying that you can't put a probability distribution, a joint probability distribution on them. And this establishes that epistemology can have an objective aspect. It can just be objectively, empirically a fact of the matter that the best possible, empirically most correct, most empirically adequate epistemic state to put in a system just doesn't contain sharp values for things, doesn't have statements about joint probabilities for all the ontic properties. System still has ontic random variables. I'll call them ontic random variables. They represent ontic things. Their values still represent the underlying values of some ontic property. There's some label A that distinguishes them. And for a given ontic random variable, it has its own private sample space. If you had multiple ones, and we'll get to this later, that are compatible in some sense, there can be a case where they share one, but I'll get to that later. For now, just think about one particular ontic random variable. It's got its own sample space, it's got its own set of probabilities. This is an individual probability distribution for that one random variable. We can define projectors just as before. They have the usual properties as before. In particular, these projectors share the same sample space as the original ontic random variable A itself. They satisfy the usual things: mutual exclusivity, completeness, eigenvalue equation, spectral resolution. But here's the new idea again. Given ontic random variables A and B, some other ontic random variable B, there may be a basic incommensurability between their individual probability distributions. There may not exist a physically, empirically accurate joint probability distribution that reliably describes their current underlying values and that yields the two individual probability distributions by marginalization formulas. For example, there could be subtle interdependencies between the two individual probability distributions. Maybe if a physical effect alters one of them, the other gets altered in some way. Already, maybe you're seeing some hints of uncertainty principle entanglement and compatible observables here, but we can phrase the possibility of these things all prior to any detailed notions of the quantum case. Well, if there's no joint probability distribution for A and B, then A plus B and AB are just not random variables because there's just no probability distribution for them generically. Now, this isn't to say they don't have underlying properties. It isn't to say that A doesn't have an underlying value and B doesn't have an underlying value. They do if they're ontic random variables. We just can't attach a probability distribution to them. There is no empirically adequate probability distribution that captures what's happening there. That can be known by any, hang on one second. right. Am I back? Can everyone hear me? Sorry about that. Okay. All right. Right. So again, this is not about ontology, it's about epistemology. All right. So the key idea, though, is that we can still define a formal algebra. We can still formally add and multiply these things together. We can still consider formal state maps, mappings from this algebra to the real or complex numbers that have the usual interpretation of expectation values when acting on an ontic random variable A. Now, the complex numbers you get from these statements may not have a clear statistical interpretation, but they still are numbers. There's still information stored in there. And we'll see that information relates to the interdependencies between these things. Notice that if we choose a set of state maps, such that whenever you see A times B appearing in one of them, you always get the same answer as if you had BA plus C, let's say. If this is always true for all the state maps in the set of state maps that we're choosing, well, then we can say that AB equals BA plus C for all purposes. More generally, we can generalize this to more general functions. If a function of AB, whatever, in all state maps always gives the same answer if I replaced F with some other function G, then we have these algebraic relationships. So our set of state maps on this formal algebra dictates the commutation, non-commutation algebraic structure of this formal algebra. So this is a sense in which we have these ontic random variables, and the state maps and the information contained in them are part of how we go from this ontic structure to being able to say things about information about the things themselves, their relationships, and the rules they obey. So suppose we pick a set of state maps satisfying the same desiderata as the classical case. There is one additional subtlety here, which is that at the level of just our original formal algebra, if I were to replace every product that looked like A, B, C, with its exact reverse, every single, I just took the whole algebra and I literally replaced everything completely the oppositely. This is at the level of the formal algebra and isomorphism. And so this motivates, you don't have to take this seriously, but for me at least, this motivates the idea that somehow you shouldn't get different information when you do this transformation. That doing this transformation should only give you redundant information. You can't take the state map to treat these things as being exactly the same. If you did that, you just get back commutative algebra. If you choose your set of state maps to have the property that when you do this replacement, you get the complex conjugate that you had before, this leads to the star involution map being product reversing. You can introduce a norm as before in terms of the spectrum of each of these operators. You could include limit points of Cauchy sequences, and what you get is a C-star algebra that generically is non-commutative. Non-commutative C-star algebra, set of state maps with the desiderata we talked about before, out's going to pop a Hilbert space. We again have this basic GNS dictionary that relates state maps acting on elements, ontic random variables, to the Hilbert space picture of sandwiching operators between the kets and bras. In particular, if you have an ontic random variable and it's got a projector and its associated operator in the Hilbert space story is rank 1, then the usual Born rule pops out of this without having to be posited a priori. You can also easily show that if the state map, if a specific state map that you're considering assigns a particular ontic random variable a trivial probability distribution, then it's just a standard, vector linear algebra exercise to show that the system state vector has to be an eigenvector of the corresponding linear operator, and this is the eigenvector eigenvalue link. Time evolution. I don't have time to go into great detail about this. I'm running a little short on time, but let me just say that if you consider automorphisms of the C-star algebra, changing around the elements of the C-star algebra in a way that preserves all the probabilities encoded in the system state map. I take this to be what I mean by information conserving evolution. Well, then there's a theorem that this is equivalent to a unitary transformation of the associated Hilbert space. In particular, if you've got a smoothly parametrized sequence of such information conserving automorphisms, you get a smoothly parametrized sequence of Hilbert space transformations. And if the assumptions of Stone's theorem hold, you then get a Hamiltonian, you get the Schrödinger equation. We can see already that there's going to be trouble with joint probabilities. If the projectors associated with two different underground variables don't commute, well, then the thing we would have computed in the classical case that gave us joint probabilities is going to be complex valued. It won't even be real valued. So right off the bat, like in our face, there is a breakdown of certain joint probabilities existing. And there's really no way to fix this. You can't take absolute values to solve this problem because then you'll spoil the marginalization rules. You can't try to redefine things in a way that removes the ordering ambiguities, because then you don't get non-negative results. You just have to bite the bullet that some statements you'd like to make about joint probabilities don't exist when things don't commute. And again, at a deeper level, what's happening here is that if projectors associated with subsets of different incompatible sample spaces for incompatible observables, they don't commute, this is an obstruction to the set theoretic picture because set theoretic intersections have to commute. So what are the lessons here? Well, the door is open now to the notion that joint probabilities can simply fail to exist objectively as a fact of the matter. In the Platonic interpretation, we extend this lack of valid joint probabilities to the case of a state map that's not separable. So to be separable means that relative to a pair of elements of our C-star algebra, is the statement that the state map covering the two of them can be decomposed into a sum of factorizable state maps with non-negative coefficients. That's separable, and for those who are familiar, that corresponds as closely as possible to classical correlation. But generically, that won't be the case. And when it's not, it means there's entanglement between them. And when there's a breakdown in separability, I take that now to mean that there's a breakdown of correlation between them. But what I'll show later is that when the environment comes into the story and decoheres things, you can get separability arising almost exactly, and it's exactly in this step that classical correlations show up and joint probability distributions show up. But again, this emergence is happening at the epistemic level. It's a statement about joint probabilities existing, being empirically adequate, not a statement about things not having ontic properties to begin with. Let me quickly go over the classical measurement process and then we'll set up the quantum process and we'll see that there's very close correspondence between them. So in the classical measurement process, we've got a subject system. I'm going to simplify things dramatically to keep things simple and to keep in time. But we have some feature A, some ontic random variable we would like to measure with its own underlying values. There's a measuring device with a pointer variable or dial D with its own values, and an environment E. It's got its own underlying variable E with its own underlying values. Initially, the measuring device has a known starting ontic underlying value. The environment has a known starting underlying ontic value, just to keep things simple. But they don't know the underlying value of A, the thing to be measured, so they have to use a non-trivial state map. This is all classical. The state map is just a simple positive convex combination of trivial state maps. The omega A's are saying the subject system is definitely in a particular label little a, and we have a blend of them, a classical probabilistic blend with probabilities. This has a positive entropy, positive Shannon entropy, characterizing the fact that there's information hiding in this subject system. The overall state map is factorizable, uncorrelated. Then the measuring device goes in and measures the underlying value of A. But now the overlying state map has a classical correlation between A and D, between the subject system and the measuring device. And this is just given by a separable, classically correlated state map. That's omega prime AD. And there's a growth in correlational entropy. The Shannon entropy of the measuring device and of the joint measuring device and subject system, all of them have increased and they're equal to the original entropy of the system to be measured. And this allows us to, characterize the flow of information. Of course, the environment quickly joins the classical correlation. The environment becomes classically correlated as well. Now the environment's entropy also grows, and the whole system has the same, all the entropies line up. Now there's two different views that one can have, and I think this is a key point. The measuring device itself has an insider view. It knows now, at the end of the process, the specific underlying value of the system's ontic random variable. If there were a passive observer, right, who does not participate in this process, embedded somewhere in the environment but stays shielded off from what has been discovered, this outsider person does not know the underlying value of A. So whereas the insider view, in Wigner language, Wigner's friend, the measuring device, The insider view would use an updated state map that identifies the specific value little a. This is omega prime prime little a. It's a trivial state map that assigns the definite label a to the subject system's ontic random variable, and they would use that to make further predictions about the subject system. But the outsider view is still going to be using the old non-trivial state map. So we see here right away that state maps collapse classically, but only for the insider view. For the outsider view, they don't. State maps are, at least classically, clearly subjective perspectival things. But this subjectivity, this perspectivalism is epistemic. It's not saying that the ontic nature of the subject system fundamentally depends on which observer we're talking about. And a final important point is that the outsider view, although using a non-trivial state map, there should be a basic compatibility between the predictions of the insider and outsider views in the sense of a suitable ensemble average over the outsider view's epistemic probability distribution. Okay, now let's talk about the quantum measurement process. And for this, I've always been very inspired by this quotation from Perez, that quantum phenomena do not occur in a Hilbert space. They occur in a laboratory. All right, so the setup is going to be very similar. Subject system, measuring device, environment. Initial state maps, known state for the device, known state for the environment. But because we're going to do something different from the classical case, now I'm going to consider a quantum superposition. I'm going to consider a state map for the subject system that in the Hilbert space language would correspond to a coherent superposition. I'm ignoring complex phase factors here, just keep things simple. So the coefficients just square root of what we would call the probabilities. The overall state map starts out factorizable, uncorrelated. This is all like in classical case. The measuring device goes in, measures A. Now the overall state map has direct entanglement between A and D. Zurich, at least, maybe people before him referred to this as the pre-measurement step. So now we have a non-trivial state map for the subject system A and the measuring device D. They're still factorizable from the state map of the environment. The state map of the subject system and measuring device together have this entangled corresponding state vector in the Hilbert space language. Notice that this state vector has vanishing entropy. To me, this is a strong signal that we're just not talking about classical correlation at this point. We're not, something very non-classical is going on here. It's a pure state vector. It has vanishing entropy. And the Platonic interpretation says, well, take that seriously. Don't assume at this point that there exists a valid joint probability distribution for A and D. But then the environment quickly joins the superposition. Now we have full entanglement between all three systems. And now at this point, if you have a very complicated environment with lots of degrees of freedom, and you compute the state map of just the subject system and the measuring device alone, what you'll find is that now they have, to a very, very good approximation in a very, very short amount of time, they have what looks like a separable state map, just like in the classical case, with the usual properties, usual entropies. So the statement is that now they have the standard correlation between their underlying ontic properties. So it's at this decoherence step when the underlying value of D, its ontic value, lines up with the underlying value of A. It's like students cheating on an exam, right? This is the moment when they get their answers lined up. It's at this step in particular when the famous non-locality of quantum theory can jump in, and I'm just going to bite the bullet on that. It's not clear that any other interpretations in a satisfying way eliminate the non-locality problem. However, there are some more serious no-go theorems that make statements that certain things beyond non-locality just can't happen. Koch-Specker, the PBR theorem, but they all depend on treating entanglement as if it means that at that moment that things are directly entangled, there is classical correlation, there are joint probabilities. So they're all evaded, they're all avoided. However, the ones that make claims about non-locality, like GHZ, those hold, and so there's non-locality in the story. As in the classical case, there's insider views, outsider views. Measuring device is the insider view. A passive hypothetical other observer has an outsider view, doesn't know the final results. So the insider view is again like Wigner's friend. That person would use a trivial state map. They know the underlying value. They would use it to make future predictions about A. The outsider view would use a decohered state map. Environment has come in, it's decohered everything to the extent that we have valid classical-ish, joint probability distributions. That's the extent to which decoherence has rendered the relevant state maps decohered and looking separable. So to that extent, the outside observer has this decohered state map, and we use this to make future predictions about A. But we have exactly the same ensemble average compatibility between these two pictures. The inside observer would reassign a new state map, would conditionally update it. This is the state collapse, but it's epistemic subjective perspectival process. The outsider view wouldn't do this. But again, because after decoherence, these probability distributions line up in this nice separable way, again, the outside observer would make predictions that should be compatible in the sense of ensemble averages, just like in the classical case. So according to Platonic integration, as I said before, decoherence is a physical process that generically realigns onto properties, but collapses subjective epistemic conditionalization. It lets the insider view make better informed predictions using whatever dynamical rule is most applicable. The inside observer would use the Schrodinger equation if the subject system is thereafter a closed system, or some suitable master equation, or semi-classical methods if all the systems in question are big and classical. Right, so we've talked about Wigner's friend that was implicit in the discussion before. I believe any interpretive program about quantum foundations should directly confront Schrodinger's cat, take a stand on what's happening, and I will. Schrodinger's cat is always ontologically alive or dead, right? That's completely compatible with the story. Opening the box and allowing the environment to decohere everything merely reveals the answers to us. So, conclusion. This is a quotation from Aesop fable. This is the one about the dog and the food the dog has in its mouth. The dog looks down in the river, looking down over a bridge, sees another dog with another piece of food in its mouth, and tries to get that food and loses the food it was eating, right? So beware lest you lose the substance by grasping at the shadow. So each quantum system has an ontology, an ontic state consisting of ontic properties, and these are the things probabilities are probabilities of. They could be positions momenta if you're considering a system of mechanical particles, like I've said before, local intensities, rates of change for a field theory. Each system has an epistemology, an epistemic state consisting of the degree to which those underlying values are manifest in the external world. Again, you could take a frequentist point of view if you prefer, and these are encoded in individual probability distributions and their interrelationships. These ontic and epistemic ingredients follow a complicated but ultimately summarizable nomology. Those are the laws or rules. We can encode all these ontic properties and their individual probability distributions mathematically in the language of ontic random variables. We can codify the individual probability distributions, their detailed interdependencies, their rules in terms of a set of state maps that determines a C-star algebraic structure on the set of ontic random variables. The original choice of ontic properties must be such that it generates an empirically adequate C-star algebra that does put some constraints on what we could take our ontic properties to be. And we can now say that joint probability distributions exist when they're not obstructed by non-commutativity or direct entanglement. That last criterion about needing the absence of direct entanglement to allow for joint probabilities to exist is a novel ingredient that threads the needle of many of the no-go theorems. Given a C-star algebra and a set of state maps for the system, the GNS construction automatically yields a Hilbert space picture, which is understood from this framework as being a useful software layer. There's no need to reify or attach direct meaning to wave functions, just like we shouldn't read too much into canonically transformed phase space variables in the classical case, or Hamilton's principal functions, or Hamilton flows, or symplectic manifolds, or non-commuting Kupeman von Neumann operators. To quote, this is a famous quotation probably that people have heard. This is the old analogy about not confusing a map with the territory it represents. What about hidden variables? Are we using hidden variables? Well, from our perspective, we're starting with ontic properties, and the Hilbert space picture, that's the hidden variables. That's the sort of mathematical set of contrivances that are very useful. We're not taking the Hilbert space picture as a given, treating it in some, trying to interpret it in some metaphysically realist way, and then adding additional variables on top. So contrast data interpretations. There's no Heisenberg cut. There's no special parameters like the GRW approaches. There's no modification to textbook quantum dynamics. There's no privileged status for agents. They're not treated separately outside of the formalism. We don't reify wave functions. There's no need to stare at state vectors, look at their branches, and try to make sense of them. There's no need to make sense of probability in a framework where every allowed outcome occurs. It doesn't. Probability is treated so sort of normally in this way. There's no need for ad hoc guiding equations or reified pilot waves. You just use quantum dynamics to predict what systems will do. There's no need to derive ontology from the configuration space that wave functions live on. So there's in fact no trouble assigning an ontology to fermatic fields. Fermatic fields have expectation values in standard Fock basis states that are just complex numbers. So we just declare that their object properties are complex numbers, just like for bosonic fields. And that's it. Thank you.
Thank you very much, Jacob. That was great. So I will take questions if people want to use the raise hand function. And if you have a sort of direct follow-up on a question that's been asked, then send a message in the chat so I can sort of slip you in. Okay, so Jeremy.
Thanks, Jamie. Jacob, thanks so much for the talk. This is really interesting and really cool, and I'm like sympathetic towards parts of it, I think, but I have really deep worries, and hopefully I can articulate them clearly. I think I have like a worry at the level of, am I understanding the project, and a worry at the level of what the project is trying to do. So the quick thing to say at the level of my understanding of the project is, towards the end, I was thinking, oh, this sounds a lot like Ravelli's relative interpretation, right? Relative state interpretation, except for replacing Hilbert space states with C-star algebraic states. And we're giving it an epistemic read rather than an ontological read. But then I was thinking, oh, but like how much weight is this new epistemic read adding? Like, okay, the epistemic read has to do with the probabilities and the joint probability distributions. But how's that epistemic? What are probabilities? You said you're punting on the question of how to interpret probabilities, and that's where I kind of got a little lost. So I would like to hear more about that, but I do want to very quickly, if I can, just say my broader concerns. I am like a really flat-footed populist about interpretations of quantum theory, right? Like I like one thing that interpretations can do, and it's not the only thing interpretations need to do, but one important thing that I think they can do is give like a tangible picture, you know, that people can grasp, you know, ordinary Joes can grasp onto, that will still be there when they're working on honing their knowledge of the structures that are telling them how to calculate and get the empirical results that we care about, you know? And you know, like love them or hate them, I can see how some of the traditional interpretations achieve this goal, you know? We have, you mentioned earlier, like Wallace tells you, oh, all the branch vectors exist, but what does that mean? What if well, like he tells you, you know, they're properties that you assign to roughly fields that are localized in regular old 3D space. So you have an ontology that is like pretty much like what the classical ontology looks like. And this is like sort of a tangent about probabilities, but like a very productive way to view the Deutsch-Wallace theorem is that it's showing you how you get the strange probabilistic structure from good old classical probability theory. But this is maybe a tangent, right? But on the contrary, right, you're presenting the C-star algebraic structure and saying like, oh no, like start here, take that as primitive when we're rejecting this paradigm. But I just don't know how to do that, you know? Like I was introduced and learned about C-star algebras as like these things are interesting because they tell you about the common structure between different ways of formulating quantum theory in Hilbert space, you know? Laura Ritchie does a great job of describing this view in her
big fan of her book.
Example, right? Yeah. And so I'm left in this place where I'm like, okay, we have this structure that is already derivative of quantum spaces, you know? So it seems like it's not a primitive thing that is helpful for the average Joe. But also like, we also have these other programs within quantum foundations that are trying to make sense of things with the usual 3D ontologies and good old classical probability spaces, right? Like this is all what GPTs are doing. And when we just saw this talk from Emily Adlam a couple of weeks ago, that was very clearly, you know, explaining how that's going, right? And so I'd like these things to meet up, and I'm not sure where running to C-star algebras, like how that's going to achieve those goals, basically. So those are the two different levels of worries. Sorry, that was a lot. Hopefully something was communicated.
It's okay. If one's going to propose an entire interpretational program, that's a big thing. This is not, you know, I tried to be, as I said, humble about some things. Like I'm not going to take on the entire problem of the philosophy of probability, you know, but, you know, when you lay out an entire framework, you have a lot of degrees of freedom exposed to the environment. There are a lot of places where one can make entirely valid critiques. And this is a program that's still, I think, in early stages. So I definitely have to think more about some of these things. What I would say is, the first thing is I don't regard the C-star algebra story as primitive. And I hope maybe I didn't make that adequately clear. What I'm taking to be primitive is that you've got systems, they've got ontic properties. The ontology is very similar to the classical case. If you've got a system of particles, what's ontic is you've got positions and momenta for the particles. The question is, how do we characterize what we can know about those properties? And how are what we can know about this property related to what we can know about this property? And what are the laws that govern how those things will evolve? I'm pushing all of the weirdness of quantum theory into the epistemic gnomic sector of the story. The rules are complicated. They're just very complicated rules that are not classical. They don't work the way we would expect classically, but we can still codify them. We just need to codify them with a more complicated mathematical language. So, that's sort of where I'm coming from in this point of view. And as far as the probability question goes, I don't fundamentally understand, probability in a rigorous way. I'm familiar with, the Dutch book type arguments and the rationality, arguments that underlie, these sorts of approaches to deriving probability theory, but I don't believe them. When you read the fine print and look at the assumptions that they start with, I find the assumptions very hard to take seriously. But that's just me. I mean, it's hard to persuade somebody of axioms, right? You either accept them or you don't.
I suppose so. Can I follow up briefly?
Sure, yeah.
I suppose so. I guess, to turn this like what was meant to be a friendly line of questioning into maybe a less friendly line of questioning is like at
oh no,
this stage,
I'm sorry, I didn't mean to transgress. Okay.
No. Well, I was just gonna say, like, at this stage, I would want to ask, like, well, now I want an alternative. I'm all for the fact that you can do this. I'm all for the fact that you can nomically specify a deviant epistemology in this way, but what's the epistemology? What's the story that is meant to motivate me to accept these axioms?
At this level, the statement is there is a set of rules that govern how the epistemology is supposed to work and how the ontic variables are supposed to change, and those rules are described by a mathematical apparatus. In some sense, this is not altogether different from taking the canonical variables in a Hamiltonian phase space, and there's a whole complicated mathematical apparatus such as symplectic manifolds and Hamiltonian flows and so forth that characterize how those things change. It's more complicated. We use C-star algebras and state maps to do it.
Yeah, but again, like, right, like I have a historical and physical narrative for how we got from observation to Hilbert algebras to C-star algebras, right? Via some of the sources that I had before,
Sure,
and I don't have that narrative here.
That's entirely
I need
fair,
that. I need that narrative before I'm going to jump on board.
Yeah. So what I'll say is, I'm somewhat limited in the scope of a 1-hour talk to explain this in more detail. Obviously, there is, a very long set of drafts and papers that go far more into depth on this that I can't do justice to here. But it's an entirely fair, statement. We have, again, a historical narrative. It's been around for 100 years, where we think we understand how we get from the empirical stuff, observations, to this Hilbert space picture, and then we abstract this to the C-star algebraic picture if we so choose. I'm subverting that historical narrative. I think subverting historical narratives is a philosophically wholesome thing to do.
I think that's fine. I just want some narrative to replace it with, but that's okay. Yeah,
that's entirely fair, and I should probably do a better job on that. Thanks.
Carl?
Thanks, Jacob. I really enjoyed the talk. I had some similar concerns to the ones Jeremy just expressed, but particularly as a philosopher who's written a lot about probability, I was disappointed when you punted on that. But the one remark you did make was that gestured in the direction of frequentism and having a connection between probabilities and frequencies out there. But the thing is that insofar as you have an ontological picture in which you've got things just have properties out there, and we think of probabilities of those properties in terms of frequencies, then the joint probability distributions always exist. That's just the way frequencies work. So, so there's something different going on. And so in the talk, I kept thinking, no, he really doesn't mean that. All his probabilities are epistemic, really. They're epistemic probabilities for observers or the environment person. And that's fine, but then I had trouble seeing what you're really doing that much different from a cubist or someone else who treats quantum mechanics fairly instrumentally. And I mean, just saying that, yeah, there are properties out there, to me doesn't say enough and about what differentiates, why is, if there is such a thing as a dynamics governing the evolution of the world, what is that, and is the observer part of it, or is the observer separate from that?
Oh, so I should say right away, the observer is absolutely part of it. I mean, I put the measuring device directly into this formalism. And at the end of a measurement process, after decoherence causes the state map to become separable, there is now a correlation between the underlying ontic value of the detector or observer's state of knowledge and the thing being looked at. So I'm putting the observer directly into this story. It's definitely not treating agents or observers, and I hope I made that clear in the talk. I very much am not taking that point of view. As far as probabilities, yeah, I mean, like I said, probability is a deeply mysterious and confusing subject to me. You know, making sense of quantum theory and fully making sense of what probability, that's a very tall order. You know, it's not something that we expected in statistical mechanics. We were able to accept and use statistical mechanics with obvious areas of metaphysical murkiness, absolutely, without fully having a rigorous understanding of probability theory. And if I can just get quantum theory to something close to that picture, with probability still a little bit murky, I still think that's progress. It's not a complete, total solution to everything, but at least it's progress. As far as frequentism goes, you know, I defer to your knowledge about, probability, and its meaning, absolutely. You know, what I would just say is, you can take a point of view on frequentism that the definition of a frequentist probability is that you literally go out and you measure all of these things and you just calculate fractions, and that's what you mean. But, if you think of probabilities, of frequentist probabilities in the sense, of, what could I go and see if I could somehow know these underlying values? You can set up weird systems where they just don't converge to well-defined probabilities in the long term. And these aren't novel to me. These are results that, I just was reading a paper from someone who was considering an example like this. It was similar to an example I came up with. I mean, you can imagine some crazy coin that when you flip it, it just increasingly diverges from anything that would be able to allow you to assign it a long-running frequency. So I don't know. I mean, I'm punting on this because it's just too big of a problem, and I would like to bite off one problem if possible. I think when you get too used to trying to derive probability from quantum mechanics in sort of Everettian or decision theoretic or rational or Dutch book type arguments, I think you get a little greedy and you begin to expect that we're just going to solve all these problems all at once. And I guess I would just propose, at least from my point of view, I'd like to be just a little more humble and not try to solve all these problems at the same time.
Mm-hmm.
But it's entirely fair. It's absolutely a thing that I need to think more about. So it's a great question.
Can I follow up, or if no one else has a question? It's just about, I was thinking about joint probability distributions in connection with Bell's theorem. And so I'm wondering whether in your framework, the starting conditions or the premises of Bell's inequality are all satisfied or not?
They're not.
So which premise is the one we give up?
The original, formulation of the Bell inequalities involves an assumption that there is a joint probability distribution over the hidden variables. And, from this point of view, instead of regarding those as hidden variables that are added onto the quantum formalism, they're ontic states, they're regarded as the underlying ontic properties. And when there's entanglement between the particles in the Bell setup, that joint probability distribution P of lambda simply doesn't exist. It comes into existence after decoherence, at least for the ontic properties in question. But this doesn't eliminate all. I mean, many people, no one here, of course, we all know this, but oftentimes people will elide the distinction between Bell's original theorem, the CHSH inequality, the GHZ no-go theorem, and that critique of the original formulation of the Bell inequality does not attach to the others. And so you do get non-locality that shows up, and I bite the bullet on that.
Yeah, okay.
Jeremy, did you have another question, or is your hand just still up? Okay. Are there any further? Julius? I can't hear you. I don't know.
Am I?
Oh, I can hear you now. Good.
It should be better now.
Yeah.
Sorry, overdetermination. Thanks. That was a fascinating talk, and I think I really see the motivation coming up for this thing coming from the Kupeman for Neumann formulation. I think to me that's like the strongest. That's a very strong part of motivation for your program. And so I'm broadly sympathetic, and I just have two clarificatory questions, simply because this is like so new to me. So the first question is, so some interpretations like the GRW lead to like predictions which in a way could be tested, right? We have a tails of the distribution problem. So in that sense, they're more like a reformulation, I would say, rather than interpretation. And what I wanted to ask is whether the Platonic interpretation is like that, or what? So whether it does or could give us some sort of predictions where we could try to pinpoint whether we live in a world described like this, or some other alternative interpretation. Like in principle, we could, in the case of GRW and BOM. And my other question is, so we started with the C-star algebras, but in some physical contexts, we work with more general objects. Like in perturbative QFT, we work with broader class of objects. How flexible is the Platonic interpretation when it comes to those choices?
Those are fabulous questions. Let me take them in order. The answer to your first question, and I address this in the working draft that I'm working on, about whether this interpretation is an interpretation, or if it's like a modification that would lead to maybe empirical discrepancies with standard quantum mechanics, like GRW. The answer is, as far as I understand, no, it is totally compatible with what we would predict from orthodox quantum mechanics. And that was part of the point, right? So, the question here is not, can I come up with a theory that is empirically testable that's different from quantum theory? The question is, if we take the standard quantum prescription, for making predictions using the framework of quantum theory, if we take that as a given, can we paint a picture of a world with an ontology that underlies it? Is there a way the world could be so that that framework is in fact the empirically adequate framework? That's what I was intending to do here. So honestly, I would kind of regard it as a bug, not a feature, if it made discrepant predictions from quantum theory. In a sense, I'm not trying to do science exactly here. I'm really trying to do philosophy, although the case has been made by lots of physicists, including Einstein, that physicists should care about the way the world really is. So I think it answers, from my point of view, what I'm trying to do with regard to your first question. Your second question about how flexible this arrangement is, and the answer there is I don't fully know. Algebraic quantum field theory at this point, I think it's safe to say, does not adequately encompass phenomenological models of particle physics. And I am deeply, deeply sympathetic to effective field theory. I mean, this is a lot of what my knowledge of physics was built on top of. So the truth is I don't fully know. Effective field theory is difficult to make mathematically rigorous, to say the least. And my hope is that there is a sense in which we could understand effective field theory as some sort of approximate quantum model that that like a coarse-grained approximate notion of a quantum theory, where we could assume that underneath it is something that is more proper and rigorous and has something like a C-star algebraic structure. And that effective field theories could be regarded as more phenomenological models and not something that need to be directly ontologically interpreted exactly as they are. But I'm not 100% sure.
No, that's a very fair answer. I guess what I'm worried here is that and sort of already in the introduction you invoke the GNS construction that kind of naturally gives us C-star algebras. But if it turns out that for whatever reason we need to work with larger class of objects, then we may not have the GNS construction. And if so, then I don't know what to do with the Platonic interpretation.
Well, then I guess what it means is that maybe we could take the answer to the second question and apply it to the first question. Maybe this does mean that in some sense it is falsifiable. If we discover systems that we can somehow describe with some kind of quantum-like framework or something else that are not compatible, that we can show are not compatible with what goes into Platonic interpretation, then it's falsifiable.
Yeah. Cool.
I'm just not persuaded yet that we have a firm enough grasp on quantum field theory, on effective field theory, to be able to answer that question.
Right, and I wouldn't like to claim that we have. It's
Right.
just the choice of the object to work with is something that that potentially concerned me.
Well, but let me just say more broadly.
Yeah.
It could always happen if you have a physical theory that you think is the right theory, and you attempt to interpret it, and then one day you discover empirically that it's not the right theory. Yeah,
Right.
that could always happen. That's the risk that we take. I'm just, I'm a risk taker by nature. I take risks all the time as long as I know everything is going to turn out right in the end.
Yeah. Cool. Thank you.
Of course.
Are there any final questions? Okay, well then, thank you again, Jacob. This has been wonderful.
Thank you very much. Thanks for the invitation.
Look forward to seeing everybody again next week. I believe we have Eric Curiel is giving a talk next time.
Very exciting. Thanks so much, Jamie. Thanks everybody for attending, and thanks for all your great questions.
Thank you. Bye, everyone.